Hello students, today we will be starting the topic mechanical properties of fluid, which is second chapter in first year NCERT. So this topic will be very interesting because this is much related to our real life. So we will be observing so many phenomena around us. So we will be trying to learn those things in this chapter. So the chapter name itself contains a word called fluid. So fluid is nothing but it contains liquids and gases. It is liquid and gases. So it doesn't contain solid, it only contains liquid and gases. So today we are going to discuss the mechanical properties of fluid, like how they behave and what are the like what are the formulas we apply to them and what are their properties. So and in this chapter we'll be going to learn one important thing called buoyancy. We'll be experiencing this so many times, like whenever we go to swimming pool or whenever we drown some jug into a bucket full of water, we'll experience some kind of upthrust. So this is what we say buoyancy. And in this chapter, we also will learn what is barometer and why it is used to do. And if you have idea about servicing of vehicles, we'll be seeing this kind of thing in the shop. And today we'll also discuss about what is this water hydraulic machines and how they are working, how we'll be able to lift such a large vehicles. And again, we'll go through different kind of flows like a streamlined flow, turbulent flow. And then we'll be learning some formulas like energy conservation, but in the case of water and fluids, which is generally called Bernoulli's principle. And we'll be going through equation of continuity and speed of efflux, Torricelli's law. What this is like, this law is about what will, like, you have a bucket full of water and you just pierce a hole in it, and what will be the speed of the water that come out of the bucket. And then we'll be learning about viscosity. So generally viscosity is nothing but it's a kind of frictional force which acts between two layers in a liquid to stop the relative motion. It's just like a friction. Like what happens in friction is, like if you are walking on the ground tries to stop you, like it tries to stop the relative motion between your foot and the ground, right? In the same way, liquids, friction in liquids we call as viscosity. So in liquid we have multiple layers. So viscosity is the force that tries to stop the relative motion between the layers of the liquid. And we have some formulas regarding that. And surface tension is another important property. Uh, if you have observed about painting in your houses, whenever we immerse painting brush into the paint, we can observe that the bristles of the brush will be floating in the water. And whenever we take out and they again become stiff. So this is the phenomenon which is caused because of surface tension of water. And we'll be also learning why water will form a concave type of meniscus in YouTube or in some tube. So let's jump into the exercise, and I will be explaining each and every topic that involved in the problems very clearly, so that you can understand each and every topic in the entire chapter. So starting with the first problem in the exercise, and these are some kind of theoretical questions, and I will just say you the fact behind that so that you can understand it. Uh, the first question, it says the blood pressure in humans is greater at the feet than at the brain. Yeah. So we all know that there's a formula called P naught plus rho g h, right? So whenever we go towards the ground, pressure keeps on increasing. And another example for this is, suppose if you have observed about scuba diving, whenever some divers go deep into the ocean, they feel some kind of pressure on them. So this is due to the phenomenon of increasing in pressure because of height. So the pressure is related to height in the via this formula, like P equals to P naught plus rho g h. Like you have 2 points, one point is above the other point. So the 2 points, distance between 2 points is h in vertical direction. So when you move from upper point towards lower point, the pressure increases by the term rho g h. So this is the phenomenon why the pressure at our feet will be greater than at the brain, because our feet are lower in height when compared to the brain. And second thing is atmospheric pressure at a height of about 6 kilometers decreased nearly to half of its value at the sea level, though the height of atmosphere is more than 100 kilometers. So what he is saying is atmospheric pressure at a height of about 6 kilometers decreased to nearly half of its value at sea level, though the height of atmosphere is 100 kilometers. So again, the same phenomenon which we used in the above question, that is height increases with the height. Like if you go towards the ground, if you go towards the earth, pressure keeps on increasing. And we can see even though the height of the atmosphere is very large, but pressure only decreases by half because the density of the air will be very less. So even though for a larger heights, the pressure will be decreased only for few amount. And the next thing is hydrostatic pressure is a scalar quantity, even though pressure is force divided by area. Yeah, this is very important concept you have to learn here. So generally the formula for pressure will be force by area, and area is a scalar vector. So and force is a vector quantity. So pressure, as like we assume that pressure will also be a vector quantity because vector by scalar gives us a vector. But here is something exceptional. Coming to hydrostatic pressure, there's one law called Pascal's law. What does this law says is whenever you apply any force on a fluid, the force will be equally transmitted in all the directions. Again, note it. Whenever you apply a force on a fluid, the force will be transmitted in all directions equally. So, if you observe the statement, there is no fixed direction for the pressure. Like pressure is applied equally in all the directions. Whenever you apply force on fluid, then it will be transmitted equally in all the directions. So there is no meaning of saying it as a vector. So a vector quantity will have a fixed direction. But coming to hydrostatic pressure, it don't have a fixed direction. So we call it a scalar quantity. So this point is to be noted. It's very important. Coming to the second question, this is also a theoretical question. The first part of this question says the angle of contact of mercury with glass is obtuse while that of water with glass is acute. So here I drawn two diagrams. The first is the case of water and second is the case of mercury. Like you just take a tube which will be available in your labs and pour some water in one tube and in another tube pour some mercury. Then you can observe these kind of things in the upper layer of the glass. So why this is happening? You can see that for the water, the surface is concave in nature, but for the mercury, the surface is convex. Why this is happening? Both are fluids. Then what's the difference that is causing this is? So there are two forces called adhesive and cohesive. So cohesive forces are type of forces which occur between particles of same material or particles of same fluid. For example, if you take the example of a water, one molecule in water will be attracting another molecule in water. So this is called cohesive force. This is a kind of force which acts between particles of same material. And another kind of force is adhesive. Adhesive force is a force that acts between particles of different materials. Suppose in this case, you can see at this point, water is connected with the water is in contact with the glass, right? So at this point, glass molecules will be pulling the water molecules, and at the same time, water molecules will be pulling the glass molecules. So this is cohesive. Sorry, this is adhesive. So adhesive means it's a kind of force which acts between different particles, like particles of different materials, like glass, water, or water and air. This is cohesive. Sorry, this is adhesive. And coming to cohesive forces, it acts between particles of same material, like two molecules in water or two molecules in mercury or two molecules in the air. So here you learn two different definitions like cohesive and adhesive. Don't confuse. Adhesive means act between different materials and cohesive means force in the same material. So coming to the question, the angle of contact of mercury with the glass is obtuse while that of water is acute. So the reason is in water, adhesive forces will dominate the cohesive force. Adhesive means so the glass will pull the water molecule with a larger force than the force between two water molecules. So that's the reason why the angle will be acute. Coming to mercury, the cohesive forces in mercury will be very large. Like it means that within mercury, molecules have a greater interaction force between them. So that's the reason why in mercury we can find the angle of contact will be obtuse. So again, I'll explain you the concept of angle of contact. So angle of contact of two interfaces, I mean two fluids. Here you can see that there is a single interface between water and glass, right? So here you can define angle of contact. So angle of contact will be the angle between the tangent drawn to the surface of the liquid to the tangent drawn to the glass. I mean tangent drawn to the solid towards the liquid. So tangent drawn to the surface of the liquid and tangent drawn to the solid or glass something towards the liquid. So coming to the second question, water on a clean glass surface tends to spread out while mercury on the same surface tends to form drops. Put differently, water wets glass while mercury doesn't. Here, this is again a natural phenomenon. Suppose if you pour some water on the floor, you can see this kind of thing happening in the case of water. So this happens when you pour some water onto the floor or some glass. But mercury doesn't occupy place like this. Mercury will form a little sphere over the surface. So why this is happening? In the case of water, it is trying to wet the floor. But coming to the case of mercury, it is forming a spherical shape which doesn't wet the floor. Why this is happening? So again, so here I wrote some equation. So SSA and SSL and SLA. So these three are different kinds of forces. I'll explain each of it. So SSA will be the force which acts between the solid and the air. So here you have three different kinds of materials. So one is the solid on which the liquid is resting. So this is the solid, this is the liquid, and surroundings will be of air. So SSK will be the force acting on solid and air, like it is the interaction force between solid and air. And SLA will be the interaction force between liquid and air, and SSL will be the interaction force between solid and liquid. And since this point is at equilibrium, all the forces acting on it should sum up to zero. So by using this concept, the angle of contact, I mean theta, the cos theta equals to SSA minus SSL by SLA. So in the case of water, the interaction force between air and the solid will be greater than the interaction force between solid and the liquid. Again, I am saying the interaction force between solid and air will be greater than the interaction force between solid and liquid. I mean, SSK is greater than SSL. So obviously numerator will be greater than 0. So cos theta is greater than 0, which means that theta is acute. So coming to the case of mercury, interaction force between surface and the air, I mean interaction force between solid and air is less than the interaction force between solid and liquid, which means that numerator will be less than 0. So cos theta is less than 0. So obviously theta will be obtuse. So that's the reason why water on a clean glass surface tends to spread out while mercury on the same surface tends to form drops. So note this formula. It is not so important, but you should understand the concept behind this. You can have a look at this formula and then you can think why this is happening. You can understand easily. The next thing is surface tension of a liquid is independent of the area of the surface. Yeah. So what's surface tension? Surface tension is the force acting on a unit length of the liquid tangential to the line of surface. I mean, so as I explained in the starting of the chapter, you can experience the surface tension while you can observe painting. Like if you immerse a painting brush into the paint, then the bristles will be free. Like we can say the bristles will be freely flowing in the paint. But whenever you take off it, the bristles will become very very strict again. So this is the phenomenon which is called because of surface tension. Coming to the definition of surface tension, it is the force that acts per unit length along the line of tangent to the surface. So obviously, when we define the surface tension, we talk about the force acting on unit length, right? So there's no point of the area of the surface. We don't care about the area of the surface. We only concentrate upon the length of the surface. So surface tension of liquid is independent of the area of surface. So it doesn't matter how much the area of the surface is. I only care about the circumference or the length of the surface. The next thing is water with detergent dissolved in it should have small angles of contact. So detergent means surf excel or rin, something which we generally use to wash clothes, right? So whenever we mix detergent into water, what happens is like the threads in our clothes acts like a capillary. Like capillary means it's a small tube. So threads in our clothes acts like capillary, and whenever we mix up detergent with water and wash our clothes, what happens is the fluid which is formed by mixing water and detergent, it travels very fastly in the capillary. I mean, in the thread, it travels very fastly. The liquid travels very fastly in the thread. It means that rises very fastly in the thread, which acts like capillary. So we know that the rise will be proportional to the cos theta. Theta means the angle of contact. And since we observed a high rise in the level of the liquid in the thread, cos theta will be very high. Like those are directly proportional, right? So if rise is high, obviously cos theta should be high. So if cos theta is high, then theta should be low. Like this is like a part of mathematics. Just think it. So greater the value of cos theta, lesser the value of theta. So going to the next question. A drop of liquid under no external forces is always spherical in shape. Let me explain why it is spherical in shape, why not it is cylindrical or some conical shape. So in the previous question, we discussed our surface tension, right? What's the aim of the surface tension? Why it is coming into act? So surface tension comes because it is because of the attraction by molecules. Suppose you have a water and you have surface of water. So molecules which are on the surface of the water will experience some kind of attraction force from molecules within the water, because the main aim of the molecules will be I have to reduce the surface area of the surface. I mean, suppose you have a bucket of water and you will be having some surface, right? What happens is molecules on the surface will experience some kind of attraction force because of the molecules within the water. Like, I mean, the molecules which are inside keeps on attracting the molecules. Like those molecules keep on pulling the molecules which are on the surface. So this causes the reduce in the surface area of the fluid. And whenever you don't have any external forces and you throw some water and you don't have any external forces around it, what happens is it tries to turn into spherical shape. And if you have seen some videos of astronauts in the space, there you don't have any kind of gravity force and you don't have any kind of air, right? So if you have seen those videos, you will definitely be observing that while brushing, like while astronauts brush their teeth, the water drops which will be in the air will be of spherical shape. But coming to Earth, whenever the rain falls from the clouds, it will be of some conical shape. So the reason why those water drops are spherical in space is you don't have any external forces, and as I said, the water molecules always tend to reduce the area of the surface. And why it is spherical? Why not cylindrical or spherical or some pyramid shape? Because with given volume, only with like you have some fixed volume of water, only the sphere will be having the least surface area when compared to other shapes. So with given amount of water, the sphere will be having the least amount of surface area. So that's the reason why water drops will be in spherical shape when there are no external forces around it. And 9.3, this question will be a little theoretical question, and you can directly see it in your NCERT textbook. I will be sharing this note, so you will be you can study it from my book. I wrote on all the answers here. So going to the fourth question, explain why to keep a piece of paper horizontal, you should blow over, not under it. Okay. And so here comes the concept of Bernoulli's principle. So here I am showing you like the diagram of paper. Let's think the horizontal line is the paper, and what our aim is to keep it horizontal. So just think, if you throw a pen up, and you want it to be in equilibrium in the air, what would happen? Like there's always a downward force of gravity on any object, but I want it to remain in equilibrium in the air. So what does it mean? There should be some force from the below towards up, right? To balance the mass, we must have some force towards up. So this is the basic concept which we will be using here. The mass of the paper will be towards down. Like gravity will be trying to pull the paper down, but to maintain it in the air, we should be having some force which pushes the paper upside so that it balances the gravity and paper remains in equilibrium. And coming to Bernoulli's principle, we know that Bernoulli's principle states that in a streamlined flow, in a steady flow, between any two connecting points, P plus rho g plus half rho v square, this term will remain constant. I mean, P, pressure at that point, plus rho g h plus half rho v square. Rho is the density of the fluid, and V will be the speed of the fluid at that point. So you have two connecting points in a fluid, which is in streamline flow or laminar flow or steady flow. So you can apply this equation anywhere in the liquid. So let's take 2 points here. One point is just above the surface of paper and one point is just below the paper. So why I'm saying just above and just below is to eliminate the term of height. So both will be having same height, so there's no problem of this rho g h term. So here I shown the clear diagram of the points and the forces acting on the paper. So A is a point which is little above the paper and B is a point which is little below the paper. And on the paper there will be a force weight which is acting towards downward, and P DOW is the force which is acting from the top, and PUP is the force which is acting from the bottom. So let's apply Bernoulli's equation between points A and B. So P DOW, which is the pressure at point A, plus half rho VA square. VA is the speed of the fluid or the speed of the air at point A, plus rho GH equals to pressure at point B plus half rho VB square. VB means the speed of the fluid at point B plus rho GH. So if you observe, what we need to balance the weight, we must have a force upward, right? So what is our necessity? We want PUP should be greater than PDOW, so that we will be having an external force which will be acting upward. So PUP should be greater than PDOW. This satisfies only if VA greater than VB. Means that to have an upward force, velocity at point A should be having the greater value than the velocity at point B, which means that you should blow air on the upper side of the paper instead of down below the paper. So this phenomenon I explain you using Bernoulli's principle. So remember, this principle is applied only in streamline flow or steady flow between two connecting points. And you can easily observe this phenomenon applies in aeroplanes even. Like we'll always be wondering why airplanes will be of very huge weight and why still they are flying in the air, but whenever I jump, why I fall down. So this is the major principle that applies behind aeroplanes or some objects which are floating in air. That is Bernoulli's principle. Going to the next question, when we try to close a water tap with our fingers, fast jets of water gush through the openings between our fingers. Yeah. Again, this we have experienced during when we are children. Like if you have some tap near our home, and when we switch on the tap and cover half part of the tap, then we can observe the water will be coming very fastly. And when you remove your hand, the water will again slow down. So we can observe that if whenever the whenever we close the tap, speed will increase, and whenever we open the tap, again speed will decrease. So the major reason behind this is um, here comes the equation of continuity. Let me explain equation of continuity with a general example. Suppose there is a classroom whose maximum strength is 50 students, like only 50 students can stay in the classroom at a time. And some new student wants to join the class. So if the new student wants to join the class, some old student must have to go away from the class, right? Must have to go outside the class because the volume, the strength of the class is fixed. And whenever you want to push some object into the class, one such kind of object should also go out from the class. So this is the equation of continuity. What it happens is, in a tube which may have irregular areas, so for a unit time, the volume of water flowing through between any 2 points will remain constant. So this is the reason why speed increases with decrease in area. That is A1 V1 will be A2 V2, where A will be the area of the surface and V is the velocity of the fluid at that point. Next, the size of the needle of a syringe controls flow rate better than the thumb pressure exerted by a doctor while administering an injection. Yeah, and we all know about injections. When we feel some kind of unhealthiness, we go to doctor and he will give us an injection. And you can observe that injection will be having a syringe, and doctor will have to apply some kind of pressure on the back part of the injection so that liquid comes out from the syringe. What he is saying is the size of the needle of the syringe controls flow rate better than the thumb pressure exerted by doctor while administering a function. So will be if you observe the size of needle will be very less, the area of the needle will be very less, and as I discussed in the previous question, if the area is less, the velocity will be very high. So here, if you observe the Bernoulli's equation, P plus rho g h plus half rho v square, what I am saying is like P is the pressure exerted by the doctor and V is the velocity of the fluid. If you observe the V is having the square term, right? Like even for a small increase in velocity, whole term changes by a lot. But if you increase pressure by a little amount, the term will change only by a little amount. Just because of the square term of the velocity, even if you increase the velocity by a little amount, the whole thing will change by a lot. Suppose you have a number, let's think you have one. What I do is you just add a number 2 to the 1. What it happens? It happens 3. But you add 2 square to the 1, I mean 1 plus 4, which becomes 5. So obviously when you have some square term, it will be having more importance than the term which don't have any square. So the size of a needle of a syringe means the size of the needle will be very less. So it indirectly controls the velocity of the fluid that comes out. So if you can control the velocity, you can change this constant value by a greater amount. So this controls flow rate better than the thumb pressure. So velocity plays more important role than a pressure in a Bernoulli's equation. Next question is, a fluid flowing out of a small hole in a vessel results in a backward thrust on the vessel. Yeah, this is Torricelli's law, which I will explain in a later question. So what happens is, if you have a bucket full of water and you paste some hole in it, water comes out of the hole. So since water is coming out of the hole, is just because some the water in the bucket will be exerting some kind of force on the fluid which is coming out. And Newton's law says that for any force there will be equal and opposite force, right? Suppose if you hit the wall, your hand will pain because the wall will also exert the same equal amount of force on your hand. In the same way, whenever bucket tries to push the water outside, the water also tries to push the bucket backward. If you can observe this example, if you can observe this diagram, here the water is coming out, bucket is trying to push the water outside. In the same way, water will be trying to push the water will be trying to push the bucket backward. So a fluid flowing out of a small hole in a vessel results in a backward thrust on the vessel. Here thrust means a kind of force. So fluid will be coming in forward direction So it applies a force which is equally and opposite onto the bucket. So bucket experiences an backward thrust. Here there are two different concepts you have to merge here. One concept is to apply the Newton's law that says there will be an equal and opposite force. And the next thing is the Torricelli's law, which I'll discuss with you in the later questions. So the next part will be a spinning cricket ball in air that does not follow a parabolic trajectory. Yeah. Suppose if you take some stone and you throw it in the air, it follows some parabolic trajectory and falls on the ground. But if you can observe, if you watch cricket regularly, in case of spin bowling, like the bowlers will throw a ball, but it doesn't follow a trajectory motion. Why? Like, what's the reason behind why the ball don't follow any trajectory, parabolic trajectory, but the stone which is thrown in the air follows parabolic trajectory? Is there any difference just because it's a stone and this is a ball? No. So the main difference comes because of the spinning of the ball. If you can see the diagram here, this is a ball, and you are spinning it. Spinning. Hope you all know about spinning. Spinning means you are rotating it along with some forward direction, along with some translational motion. You also apply some kind of rotational motion on it. So suppose this is a ball and you are spinning it. So upward point will be having a velocity of Vs. Like you are spinning the ball with some velocity, say Vs. V spin means, and you have 2 points. One point is a upper point of the ball and another point B, which is the lower point of the ball. And you are having some wind. So what's happening is you go to some ground and you try to spin the ball, and the air around you will have some velocity, right? It doesn't stay still, right? Air definitely will be having some kind of velocity, and A is the upward point of the ball and B is the downward point of the ball. What happens is A will be having this additional speed of VW, velocity of Vs in the forward direction. At the same time, the velocity of wind also adds to the velocity of A. So velocity of A will be velocity due to wind plus velocity due to the spinning. But coming to B, velocity of B due to the spinning will be in the backward direction. You can observe this fact from the diagram. Velocity of B due to the spinning will be in the backward direction, while the direction of wind will be in the forward direction. So velocity of B will be VW minus Vs, whereas velocity of A will be VW plus Vs. And clearly between 2 points on the same wall, we are having velocity difference. And the immediate thing that comes to your mind when we think of velocity difference is, since there is velocity difference, there must be some pressure difference also by Bernoulli's equation. So what happens? You're not having, like, whenever you throw a stone, the only force that acts on the stone will be the gravity. But in this case, gravity is not the only force acting on the ball. Along with the gravity, there is some pressure difference between the upper and lower points of the ball, which exerts some pressure. Like here, velocity of A is greater than velocity of B, right? So pressure at B will be greater than the pressure at A, which means that upward force will be greater than the downward force. So what happens is, if you stow it thrown upwards, the only force that acts on the stone will be the gravity. But if you spin a ball, along with the gravity, along with the mass of the ball, you always have some kind of upward force. So due to which the ball won't follow exact parabolic trajectory. And until now, we all have seen the natural phenomenon, like we'll be seeing these things since our childhood, but we never notice the reason behind these things. So Bernoulli's equation plays very important role, and Torricelli's law, and equation of continuity, and again concept of adhesive and cohesive forces. So just try to apply these concepts in your natural life, and you will get the better understanding of the concept. So going to the fifth question, a 50 kg girl wearing high heel shoes balances on a single heel. The heel is circular with a diameter 1 centimeter. What's the pressure exerted by a heel on the horizontal floor? This is a basic question. This question is just to make you clear of the concept of pressure. So pressure is again force by area. The force on the heel will be the mass of the girl. That is, the weight of the girl. That is 50 kg into g. Like weight is m into g, right? Where g is the acceleration due to gravity. Weight will be m into g. And area of the heel is pi into r square. Like the area of the circle will be pi r square. And here he gave the diameter is 1 centimeter. So the radius will be 0.5 centimeter. And you can, this is a direct formula based question. Pressure equals to force by area, and force is the weight, and area is equals to pi r square. Going to the next sixth question. Torricelli's barometer used mercury. Pascal duplicated it using French wine of density 984 kg per meter cube. Determine the height of the wine column for atmospheric pressure. Okay. So here we will be discussing about the what's barometer and why we use it. I'll show it in the textbook because it's difficult to draw it. So this is the barometer. So what happens is you just take some vessel and pour some mercury in it. And what you do is you take some tube. This is the tube. The tube should not contain any kind of air, even vacuum. There should be no any kind of air inside the tube. There should be no any kind of air trapped inside the tube. So first take a vessel filled with mercury and then take a tube and completely try to immerse the tube into the mercury. So after immersing, you will get this kind of scenario. And you can see this part of the tube which is very empty. This contains vacuum. And the pressure in vacuum will always be zero. Like if you go on moon, you don't feel any pressure on your head. Right? It means that in vacuum, you don't have any pressure. So pressure at A will be zero. And pressure at B will be equal to pressure at C because those are at equal level, right? So if you observe the Bernoulli equation, here the fluid is at rest. So fluid is at rest. So we don't have the use of velocity term. And B and C both are at equal levels. So again, the height terms get cancelled. So you can get that pressure at B will be equals to pressure at C, right? So the pressure at B will be pressure at A plus rho into G into H. Just observe this. Pressure at B will be equals to pressure at A, which is 0 plus rho into G into H. So clearly pressure at pressure at B will be rho GH, and which should be equal to the pressure at C. And C is there in direct contact with the atmosphere. So pressure at D will be equals to atmospheric pressure. So atmospheric pressure is equals to rho into Z into H. So this is an experiment which we generally use it to calculate the atmospheric pressure at some point. Coming back to the question, Torricelli used mercury in barometer, just as explained. What Pascal did is he replaced mercury with some French wine of density 984 kg per meter cube. Determine the height of the wine column for normal atmospheric pressure. So value of normal atmospheric pressure will be 10 power 5 pascals. Pascals is unit for pressure, which is nothing but Newton per meter square. So atmospheric pressure will be 10 power 5 pascals, which is equals to rho into Z into H. Rho is the density of the fluid which we are using in the barometer. G is the acceleration of gravity, and H is the rise in the capillary. How much height will the fluid rise in the capillary tube? So you can directly substitute the values. Density is given as 984 kg per meter cube, and you can get the height as 10.5 meters. It means that whenever you take capillary tube and immerse it into a vessel of French wine, the fluid will rise for a height of 10.5 meters in the capillary. So this is a simple question. This is made to make you understand about the barometer and the concept behind this. And this barometer is used to calculate the atmospheric pressure. Coming to the next question, a vertical offshore structure is built to withstand a maximum stress of 10 power 9 pascals is a structure suitable for putting up on the top of an oil well in the ocean. Take the depth of the ocean to be roughly 3 kilometers and ignore ocean currents. Okay, what he is doing is he made some wall, vertical offshore structure. So let's think he made some wall and it can withstand a maximum stress of 10 power 9 pascals. Maximum stress means it can withstand a maximum pressure of 10 power 9 pascals. And what we are doing is I am taking this wall into the underground, I mean into the sea level, and I want to know whether the wall can be able to withstand with the pressure which is under the sea level. So here you can see the diagram. This is the wall. So what will be the pressure on the wall now? So pressure on the wall will be P naught plus rho g h. And if you calculate its value, it will be 10 power 5 plus 3 into 10 power 7, which is less than 10 power 9. So the wall which we built will be able to withstand the pressure under the seawater. Going to the next question, a hydraulic automobile lift is designed to lift cars with a maximum mass of 3,000 kg. The area of cross section of the piston carrying the load is 425 centimeters square. What maximum pressure would the smaller piston have to bear? So if you can see the diagram of the hydraulic machine. Wait, let me show you it in the textbook itself. Here we got it. So this is the hydraulic machine. Here you have some vehicle, you have some huge load, and here you will be having very small piston on which you apply pressure to lift the load on the other side. So you apply pressure here, and in turn this object gets lifted. So what he's saying is this piston can withstand a maximum weight mass of 3,000 kg, and this area is 425 centimeters square. Then what will be the maximum pressure that it is present at the smaller piston? So here, what's the maximum pressure that can the weight of the car? So which will be the mass of the car into acceleration due to gravity divided by the area of the surface, 6.92 into 10 power 5. This is the pressure applied at the larger piston. And as we studied in Pascal's law, what it says is if you apply any force on a fluid, it is equally transmitted in all the directions of the fluid. So in the same way, in hydraulic machines, these two pistons will be at same height. So obviously they should have same pressure. So the whatever the pressure that is present at the larger piston will be equal to the pressure that is present at. So pressure at smaller piston will be equal to the pressure at the larger piston, which is equals to weight of the car divided by the area. That is 6.92 into 10 power 5 pascals. So why we use this kind of machine to lift huge masses will be equal. That is the main reason behind this. So here we generally apply force. That is here we generally apply force. If you observe the area of this piston is very less. So even for a smaller value of the force you apply here, the larger piston experience a greater amount of force because F1 by A1 will be equals to F2 by A2 because F by A is again the pressure. Pressure at both the pistons should be equal. So F1 by A1 will be equals to F2 by A2. So even for a smaller value of F1, F2 should increase by greater value. So this is a phenomenon which we use in the hydraulic machines. Coming to the next question. A U-tube contains water and methylated spirit separated by mercury. The mercury columns in the two arms are in level with 10 centimeters of water in one arm and 12.5 centimeters of spirit in the other. What is the specific gravity of spirit? Okay, so you are having a U-tube. U-tube is not something which we see in mobile. So U-tube is a tube which is in the U shape. So here you can see it in the diagram itself. So what I did is I fill my U-tube with water, mercury, and methylated spirit. Methylated spirit is some kind of fluid. It's some kind of liquid. And here we don't need its properties. We just need its density. That's it. So this is the situation. What happened here? I mean, like the levels of mercury in the both hands of the U-tube are equal. In both sides of the U-tube, the level of the mercury is equal. So what he gave is the pressure is equal at both the points. So you can directly apply the equation that pressure at A equals to pressure at B. That is, the pressure at this point will be atmospheric plus pressure plus rho into G into height of water. That is, pressure at this point will be atmospheric pressure plus density of water into height of water into G, which will be equals to pressure at this point. That is, atmospheric pressure plus density of methylated spirit into height of methylated spirit into acceleration due to gravity. So P naught term gets cancelled on the both sides. Here you can get the density of methylated spirit divided by density of water is equals to 10 by 12.5, that is 0.8. So this is the specific gravity of the methylated spirit. Specific gravity is again the relative density with respect to water, which means that actual density of the fluid divided by the density of water gives us the relative density of the fluid, which we got as 0.8. So where are we? In the next question, in the previous problem, if 15 centimeters of water and spirit each are further poured into the respective arms of the tube, what's the difference in levels of mercury in the two arms? So in the 10th question, what he did is, in the previous question, we have 10 centimeters of water and 12.5 centimeters of methylated spirit. Now what I do is, I pour 15 centimeters of water in the left hand and 15 centimeters of methylated spirit in the right hand. So this will be the scenario now. So the height of water will be 25 centimeters because previously it is having 10 and now I poured 15 centimeters extra. So height of water will be 25 centimeters and height of methylated spirit will be 27.5 centimeters because initially it is 12.5 centimeters and now I poured 15 centimeters of spirit. So the net height becomes 27.5 centimeters. And now what I want is, what will be the height difference in the levels of mercury in the both hands? In the previous question, mercury is at equal levels in both hands. Now what happens is, I want to find the difference in height of the levels of mercury in the both hands. So again, you just have to simply equate the pressure at these 2 points. Like you remember this, you have between any two connecting points which are present in the same fluid and at same height, pressure will be equal. So this is the same fluid, that is mercury, and this point which are at equal level, pressure should be equal, right? So the equating pressure at both points, pressure at this point will be atmospheric pressure plus density of water into G into 25 centimeters. That is equals to, we need to now calculate the pressure at this point, right? So to get the pressure at this point, we first need to get the pressure at this point. So pressure at this point will be atmospheric pressure plus density of methylated spirit into 27.5 into G plus. So now I got the pressure at this point. So to this point, what I need to add? I need to add density of mercury because this part is of mercury. So density of mercury into height difference into G. So again, clearly observe this. In the right hand side, to calculate the pressure at this point in the right side of the tube, what I did is, first I calculated the point. First I calculated the point of this point. I calculated the pressure at this point, and then using the pressure at this point, I calculated pressure at this point. Why I'm separately calculating pressure at two different points? Like you say that here you directly wrote P naught plus density of water into G into 25 centimeters. Why you are calculating the pressure at this point, and then again, why don't you directly write P naught plus density into rho into, density into G into H? The main thing is, here we are having two different kinds of fluids which will be having different densities. In the left side, entire fluid is water, so all will be of uniform density. But coming to the right side, some part is of methylated spirit and some part is of water. So we need to apply pressure equations at different points. So pressure at this point will be atmospheric pressure plus density of methylated spirit into G into 25.5 centimeters. So to get pressure at this point, you just need to add this rho into G into H, where rho is the density of this part, that is mercury. And if you simplify this, then you can get the height of the difference in the levels of mercury in both hands as 0.221 centimeters. So through this question, what we learned is, we can't apply directly the pressure equation between two different fluids. So first you need to calculate the pressure at the point which is in the junction between 2 points, and then you need to calculate the pressure in the next fluid. Going to the next question. Can Bernoulli's equation be used to describe the flow of water through a rapid in a river? Explain. When I explained the Bernoulli's principle, I stated that Bernoulli's equation can only be applied in a streamlined flow. A streamlined flow means in liquid you have multiple layers and one layer should not be intersect with another layer. Like all the layers in the liquid should be parallel to each other. This kind of flow we call as streamlined flow. So Bernoulli's equation can only be applied to streamlined flow of fluid. But here they are saying that flow of water through a rapid in a river. It means that flow is very fast and it means the flow is very turbulent. Means that the layers are intersecting each other at some random points. So obviously there is no streamlined flow of fluid. And Bernoulli's equation can only be applied in streamline. So we can't apply Bernoulli's principle here. Next question is, does it matter if one uses Gauss instead of absolute pressure in applying Bernoulli's equation? So what is Gauss? Gauss is a kind of pressure. Like Gauss pressure will be equals to absolute pressure minus atmospheric pressure. What is asking is there any problem if I use Gauss pressure instead of absolute pressure in the Bernoulli's equation? No, yes, obviously there will be no problem, because if you can observe here the Bernoulli's equation, that is absolute pressure plus rho g h plus half rho v square is absolute pressure plus rho g h plus half rho v square. And if you subtract atmospheric pressure from the both sides, that is P1 minus P 0 plus this term equals to P2 minus P 0 plus this term, right? You just subtracted P 0 from the both sides, so equality remains constant. Again, this is the Gauss pressure. So again, what you're getting, Gauss pressure plus rho g h plus half rho v square equals to Gauss pressure plus rho g h plus half rho v square. So it doesn't matter whether if you use absolute pressure or Gauss pressure, but it matters like you have to use absolute pressure or you have to either use Gauss pressure. You cannot use absolute pressure on one side and Gauss pressure on the other side. Either you have to use absolute pressure on both sides or Gauss pressure on both sides. Coming to the next question, glycerin flows steadily through a horizontal tube of 1.5 centimeters and radius 1 centimeter. If the amount of glycerin collected per second at one end is 4 into 10 power minus 3 kg per second, what is the pressure difference between the two ends of the tube? So what's happening here is you have a horizontal tube and you are sending some water through the tube. Sorry, you are sending some glycerin through the tube. So why here he mentioned glycerin and why not he used water is, in glycerin you can find a larger viscosity, and I explained about viscosity. Let me explain it again. Viscosity means it's a kind of friction in the fluids which tries to stop the relative motion between the adjacent layers in a liquid. Suppose you have two layers, one above and one below, and upper layer is moving with some velocity in the forward direction, and downward layer is moving with some velocity in the backward direction. What happens is a viscous force coming to act because there is relative motion between the layers. So what I do is I want to stop the relative motion between these two layers. So a kind of force acts on both the layers that stop the relative motion. That is viscosity. And viscosity is the property of fluid which varies to the fluid. Suppose you have water, it has very less viscosity, and you have glycerin which has high viscosity. So in this example, he took glycerin and he is sending glycerin through a horizontal tube which is of length 1.5 centimeters and its radius is 1 centimeter. And what he's saying is at one end the glycerin is collecting at a rate of 4 into 10 power minus 3 kg per second. That is, in 1 second, 4 into 10 power minus 3 kgs of glycerin is getting collected at one end. And he also gave the density of glycerin as 1.3 into 10 cube kg per meter cube. So density, which is nothing but mass by volume. Using density and the mass, you can find the volume which is getting collected in 1 second. That is, volume will be mass by density. What we need to find is what is the pressure difference between the two ends of the tube. So we have a Poisson formula. What it says is V is equals to pi into P r power 4 by 8 eta into L. So V is the volume of liquid that is getting collected at one end per unit time. That is in one unit of time. That is in 1 second, how much fluid is getting collected. That is how much fluid is getting into rest. It will be equals to pi, it is constant, into P. P is the pressure difference across the two ends of the tube, and r will be equals to, r is the radius of the tube divided by 8 eta into L. Eta is the viscosity, the coefficient of viscosity, and L will be the length of the tube. So using this formula, you can easily get the value of P. So the main intent behind this question is you should be able to use the Poisson-Willis formula, like you should know when to use this formula. And another point is you need to convert the mass into volume. Like he mentioned how much mass is getting collected in 1 second at one end. You should be able to convert this mass into volume by taking the help of density. So just remember this formula and you know everything, like they mentioned everything that is required to calculate the value of P. So going to the next question, in a test experiment on a model aeroplane in a wind tunnel, the flow speeds on the upper and lower surface of the wing are 70 meter per second and 63 meter per second respectively. What is the lift on the wing if its area is 2.4 meters square? Take the density of air to be 1.3 kg per meter square. So let's think this is the wing of the aeroplane. In the previous some problem I explained like how to keep a paper in air in equilibrium. Like you should blow over the paper to keep it in equilibrium, right? So in a place of paper, if you take the wing of an aeroplane, what he's saying is the upper point of wing is having velocity of 70 meter per second and the lower point is having 63 meter per second. Calculate the lift on the wing. So what we need to calculate is how much pressure is applied on the wing in the upward direction. That is generally what we call as a lift. So lift is the force that is acting on the wing in the upward direction because of the pressure difference. You can note this definition of the lift. So lift will be equals to the force acting on the wing due to the pressure difference present between the upper and lower points of the wing. This is a straightforward application of Bernoulli's equation. You can apply Bernoulli's equation between upper and lower points of the wing. That is pressure at upper point plus half rho into 70 square plus rho gh equals to pressure at lower point plus half rho into 63 square plus rho gh. And rho gh term gets cancelled because those 2 points are almost in same height. So rho gh term gets cancelled. So the P2 minus P1 will be equals to half rho into 70 square minus 63 square. And rho, he mentioned that take the density of air to be 1.3 kg per meter cube. So rho is 1.3 and the pressure difference, that is P2 minus P1, will be half into rho, that is 1.3 into 70 square minus 63 square. So this is the pressure difference that is acting on a wing. What we need to calculate? We need to calculate the lift. Lift is the force that is caused due to the pressure difference. That is pressure difference into area will give us the lift on the wing. And area is 2.4 meters square, which he mentioned in the question itself. So you can directly calculate the value of P2 minus P1 into A. And this problem, with the help of this problem, we can understand why even though the airplanes are of very high mass, still they are able to fly in the air without falling down. So the reason is the pressure difference, which comes because of the difference in the velocity at upper points and lower points. Going to the 15th question. So here, figure 9.2a and b refer to the steady flow of a non-viscous liquid. Which of the two figures is incorrect? Okay, and why? State the reason. Okay. So here we are given two different diagrams and he is saying that one among these two is mistake. Just find out that. Okay. Okay, just observe the both diagrams thoroughly. You can, like if you observe thoroughly, then you can definitely get the idea of what is going wrong here. So let me explain this. Again, this is application of Bernoulli's equation and equation of continuity. As I mentioned, equation of continuity, that is, it states that in a tube, amount of water that travels across a point in unit amount of time will be equal. This point of water is the volume of water that travels through this point in unit time will be equal to the volume of water that travels through this point in unit time. Area at this point into velocity at this point will be equal to area at this point into velocity at this point. You can observe this. You can observe that area at this point is greater than the area of this point, right? So obviously velocity at this point will be less than the velocity at this point. That is A1 V1 is A2 V2. So if area is larger, then velocity should be smaller. So what is happening is velocity at this point is less than the velocity at this point. Here you can see this. So A1 V1 equals to A2 V2. Since A1 is greater than A2, V1 should be less than V2. So that equality will be maintained. And if you apply this result in the Bernoulli's equation, which is written between these 2 points, so pressure at this point plus half rho V1 square plus rho GH is equals to pressure at this point plus half rho V2 square plus rho GH. And rho GH term gets cancelled because those 2 points are the equal height. So V1 is less than V2, that is pressure velocity at this smaller area is greater than the velocity at this larger area. So since V2 is greater than V1, P1 is greater than P2. You can just observe this observation from this equation. P1 minus P2 is half rho into V square minus V1 square, right? So V2 is greater than V1, which means that P1 is greater than P2. So what we got from this two equations, that is equation of continuity and Bernoulli's equation, is pressure at this point is greater than the pressure at this point. If you observe, these two are capillary tubes, right? Pressure at this point will be pressure at this point, right? This is the observation we made. And you can see some amount of liquid rise in the capillary tube in the barometer case, right? So P0 plus rho GH will be equal to the pressure. Hope you remember about the barometer example which I explained, where the pressure will be obtained by getting P0 plus rho GH. In the same way, pressure at this point is atmospheric pressure plus rho GH. Pressure at this point will be atmospheric pressure plus rho GH. Obviously, pressure at this point is greater than pressure at this point, right? We got that observation here. That is pressure at this point is pressure at this point. So obviously, height should be greater in this capillary than this capillary. Again, I'm saying pressure at this point is greater than pressure at this point, which we got from the two equations. Since pressure is directly proportional to the height, as I said, if you go towards the earth, the pressure keeps on increasing. So pressure at this point is greater than pressure at this point, which means that here height should be greater than the height of the fluid in this capillary. That is, if you observe this, height of the fluid in this capillary is greater than the height of the fluid in this capillary. So this is correct because here the height is more, so pressure will be, that is calculated using P0 plus rho GH, will be more at this point than this point, and which correctly matches our observation that P1 greater than P2. So this figure, that is A, is wrong. Going to the next question, the cylindrical tube of a spray pump has a cross section of 8 centimeters square, one end of which has 40 fine holes, each of one diameter 1 millimeter. If the liquid flow inside the tube is 1.5 meter per minute, what is speed of ejection of the liquid through the holes? Again, this is the application of equation of continuity, and you can easily solve this using formula. That is 8 centimeters square into 1.5 meter per minute equals to 40 times the pi square into V, where V is the rate at which the spray comes out of the smaller diameter hole. You can just simply solve it, and if you have any doubt, you can see it from my notes, which I will be sharing with you. Going to the next question, a U-shaped wire is dipped in a soap solution and removed. The thin soap film formed between the wire and light slider supports a weight of 1.5 Newton into 10 power minus 2 Newton. What is the surface tension of the film? Okay, so this is the scenario that is mentioned in the question. So you have a U-shaped wire, and you dip it in the soap solution. So a layer of soap will be formed, and to that, so this is the layer. So this is the layer of soap that is formed. You can see this from the next question. So this is the layer of soap formed, and to this layer, what you did is you attached this. You supported a weight of 1.5 into 10 power minus 2 Newton. Okay. So this here you attach the weight of 10 power minus 1.5 to 10 power minus 2 Newton. And as I mentioned, surface tension is the force exerted by the liquid per unit length along the line tangent to the surface. So an upward force which will be equals to T into L will be acting on this, and at the same time downward force of 1.5 to 10 power minus 2 Newton is acting on it. And since it is in equilibrium, both forces should be equal. So T into L, that is 30 centimeters, which is 0.3 meters, should be equal to 1.5 to 10 power minus 2 Newton. So using this, we get surface tension will be 5 to 10 power minus 2 Newton per meter. And going to the next question. Figure 9.21a shows a thin liquid film supporting a small weight of 4.5 to 10 power minus 2 Newton. What is the weight supported by a film of the same liquid at the same temperature? In figure B and C, explain your answer physically. And clearly, in the previous question, we also learned that the surface tension doesn't depend on the surface area. It only depends on the length of the surface, right? So in here, what is asking is what will be the weight supported by the three cases? We can observe that in three cases, the surface length is 40 centimeters. So the surface tension which acts on that part will be T into 40 centimeters. So all the three cases, that is A, B, C, support same amount of weight. That is 4.5 to 10 power minus 2 Newton. Again, this question is an observation which we made in one of the previous questions, but not on the surface area. Going to the next question. What is the these two questions are a little logical and thinking. So there are the concept behind this. What is the pressure inside a drop of mercury of radius 3 millimeter at room temperature? Surface tension of mercury at the temperature is 4.5 to 10 power minus 1 Newton per meter. The atmospheric pressure is 1.01 into 10 power 5 Pascal. Also give the excess pressure inside the drop. So we have a mercury drop of radius 3 centimeters. What he is asking is, what is the excess pressure that is present inside the mercury drop? So we have a formula that inside a solid sphere means entire sphere contains material. Inside solid sphere, the excess pressure would be 2s by r, which can be directly calculated from the values given. Little direct question. So next question will be a little logic. Coming to the 20th question, what is the excess pressure inside a bubble of soap solution of radius 5 millimeters? Given a surface tension of soap solution at temperature 20 degrees Celsius is 2.5 to 10 power minus 2 Newton per meter. So here you have to observe this. In the previous question, it is a mercury drop, but here it is a bubble of soap. If you observe the bubble of soap, it only contains a thin layer of soap, and inside the bubble it will be air, and outside the bubble it will be of air. That is, it will be having two interfaces. That is, here you can observe this. So this is the thin layer of soap, and inside it will be air, and outside it will be air. Coming to the drop, it only have one interface with the air, and the entire part is inside the entire inside is filled with the material. Only outside it will be air, but coming to the bubble, inside will be air and outside will be air. Here it is having only one interface with the air, so the excess pressure will be just 2 into S by R. But here it is having two interfaces, one with the outer air and one with the inner air. That is, it is having two interfaces. So the excess pressure will be 2 times the 2S by R, that is 4 into S by R. Again, in a drop, it will be having only one interface, so the excess pressure will be 2 into S by R. But in a soap bubble, we will be having two interfaces, that is, so it will be 4 into S by R, that is 2 into 2 S by R. So you can calculate the excess pressure. And the next part of the question says, if an air bubble of the same dimension were formed at a depth of 40 centimeters inside a container containing the soap solution of relative density 1.2, what would be the pressure inside the bubble? Okay. So what he did is, an air bubble is formed at a depth of 40 centimeters inside a container containing the soap solution. Here, entire surrounding is covered with soap solution, and it is an air bubble. That is, it contains air inside. If you can observe here, there is only one interface here. That is, only one surface that is in contact with the soap solution air. In mercury drop, there is only one surface, and coming to soap bubble, we will be having two interfaces here. And again, coming to this scenario, entire part of the outside is soap solution, so only the inside part is of air, so we'll be having only one interface. So the excess pressure will be 2 into S by R, and P1, so pressure inside will be P1 plus 2 into S by R, and P1 can be calculated by using pressure, atmospheric pressure. That is P1 will be P naught plus rho g into 40 centimeters. So the pressure inside this will be pressure at P1 plus 2 into S by R. That is pressure at P1 is again P naught plus rho g into 40 plus 2 into S by R, which gives us the pressure at inside point. And which, if you calculate it, you can get the pressure at inside point will be 1.06 into 10 power 5 pascals. So students, in this chapter, we discussed about so many phenomena that is happening around us, like why a spin ball doesn't follow a trajectory path, and why bristles of paintbrush flows freely in the liquid, but when we take out it, it becomes again straight. What the reason behind this? And when we close some part of the tap, the speed of the water increases. What's the reason behind this? And when we throw some object into the water, it again comes up. And what's the reason behind this? And a huge object, that is aeroplane, floats in the air. And what's the reason behind it? So we came across several real life phenomena and some important principles like Bernoulli's principle and equation of continuity and Torricelli's law and concept of excessive pressure inside a soap bubble or drop. And we also learned the concept of hydraulic mission, which we can see in the service centers of vehicles. That is to lift huge vehicles like cars, lorries, and bikes. We use this kind of machines. And we also learned concept of barometer, why we use barometer. And we also learned why the meniscus, of that is the surface of water, will be concave while that of mercury is convex. So these general phenomenon are covered under the chapter of mechanical properties of fluid. So as I said, this is a very interesting topic, and instead of mugging up the principles and formulas, try to apply these formulas and theory on the real life situations, and you will get a better grip on this topic. So wrapping up this session, guys, and if you have any doubts, you can contact with me, and I will be sharing my notes with you. So in case if you have any doubts while solving these problems, you can refer to my notes. So thank you. Signing off. Meet you in the next class.